All right, answers to AP test review number 7. Number 1, let R be the region bounded by the graphs of y equals x squared and y equals x plus 6. So we went ahead and graphed that over here. Pretty basic graphs to graph, so we did that. And part A is find the area of R, which is just top minus bottom. So top is the line, which is x plus 6. The bottom is x squared. You have to find the intersection points. So set these two things equal to each other, which is what we did here, and solve, and we get -2 and 3. So we integrate that thing from -2 to 3, and we end up with our answer. Remember, on free response, once you integrate and plug in, you've completed the problem, so there's no need to continue on. Part B, write but do not evaluate an integral expression for the volume of a solid generated when R is rotated about the horizontal line y equals 9. So we're going around 9. Okay, so again, I need to ask myself as I'm rotating around this, is it in constant contact? Is there a gap? In this case, there's a gap, so that means I need 2 R's. I need 2 R's. And what I'm rotating around is on top, so that means it needs to come first on both R's. So for the first R, I need to know which one of the two functions is furthest away. There's the line, there's the parabola, so the parabola is obviously furthest away. So I need 9 minus the parabola, which means the other one needs to be 9 minus x plus 6. We've got pi, and we've got r1 squared, we've got r2 squared, going from -2 to 3. All right, C, we're this time our volume, and we're rotating around y equals -1. So this time we're rotating around y equals -1. Notice this time it's below my region, so that means it's got to come second on both R's. So notice -1 is coming second. Which one's furthest away from this? So there's the parabola, there's the line. The line's furthest away, so that means it has to be an R1. So x plus 6 minus a -1, x squared minus a -1. So interval is the same, -2 to 3. Don't forget about the pi, r1 squared minus r2 squared. The last one, when R is rotated around the vertical line x plus 5. So 1, 2, 3, 4, 5. So I'm going around the vertical line. That's right there. Notice when I'm rotating, again, I'm not in constant contact. So that means I need 2 R's, and the vertical line is on the right. So that means it has to come first. So 5 comes first. And also, this is a tricky one because when I do right minus left on the top is the parabola minus the line, but right minus left down here on the bottom is the parabola minus the parabola. Since I'm going around something that's vertical, I need to solve for x on both of them. So here's the parabola. When I solve, notice it's got plus and minus. So the plus is going to be the right side of the parabola. The negative is going to be the left side of the parabola. And then my other one is y minus 6. So let's see, which one did I do first? I did the bottom part of the parabola. Okay, so 5 needs to come first, and then the furthest one away would be the left side of the parabola, which is the negative square root. So 5 minus the negative square root, and that means the other one is 5 minus the positive square root. So that's 0 to 4, r1 squared minus r2 squared dy. Then for the top, 5's got to come first. The line is furthest away. So my line is y minus 6. So I've got the 5 minus y minus 6. And the right side of the parabola is second. So 5 minus the square root of y. So I got r3 squared and r4 squared. I'm missing the square right here. That should be squared. All right, next one. Limit as I'm going to infinity. You can remember your rules on this, or you can do L'Hopital's rule, either way. But if I were to multiply this out, the negative x times this gives me -2x squared. The x times this gives me x squared. If you remember, if you're approaching infinity and the highest exponents are the same, then that means you take the coefficient. So I've got -2 over 1, which gives me -2. Same thing is happening on this one. I'm going to infinity. I've got an x cubed and an x cubed, so I take the coefficients, and it gives me a over b. Looks like I didn't finish 4. So on this one, we want f of x is cosine of x. Again, take the parenthesis away, put x in its place. There's f. Then we want to take the derivative of this. So the derivative of cosine would be negative sine, and then we stick the pi over 2 in. So negative sine of pi over 2. Sine of pi over 2 is 1. With the negative, the answer to this thing should be negative 1. Number 5, we want the derivative, and we want to plug in pi over 9. So derivative of cosine 3x is negative 3 sine of 3x. Plug in the pi over 9, which reduces to pi over 3. Sine of pi over 3 is the square root of 3 over 2, and then we have that coefficient of negative 3. 6, find a and b so that f is differentiable everywhere. 4a plus 1, or so differentiable everywhere. So if I'm differentiable, that means it's also continuous, which means the limits as we approach 2 have to equal each other in this case. So I'm going to plug 2 in, which gives me 4a plus 1, and I'm going to plug 2 in, which gives me 2b plus 3. So because it's continuous, when I plug 2 into both of these, they have to equal each other. And since it's differentiable, that means I have to be able to do the same thing with the derivative. So I take the derivative of ax squared plus 1, which is 2ax, and bx minus 3, which is b. I plug 2 into both of these and set them equal. So I plug 2 in here, it's going to give me 4a. I plug 2 in there, it's going to give me b. So I get 4a equals b. So since b equals 4a, I'm going to come back over here. I'm going to take the b out. I'm going to plug 4a in, which gives me 8a. I'm going to subtract the 4a over. I'm going to add 3 over, which gives me 4. So we find out that a is 1. Once we figure out a is 1, we plug a in over here, and we see that b is 4. Number 7, we want to evaluate from negative 3 to 3. Since it's a piecewise, notice it jumps at 1. So that means one of my integrals has to go from negative 3 to 1, and the other one has to go from 1 to 3. Since this is less than, we need negative x to go where we're dealing with numbers less than 1, which is right here. So that's why the negative x is there. That's why x squared minus 2x is here. Then it's just a matter of integrating and plugging in for both of those. Not much going on there. Remember, I could have stopped right here if I wanted to. Once you integrate and plug in, you have completed what they want you to do. All right, number 8. Let R be the regions bounded or region bounded by y equals the square root of x and y equals x over 2. So I graph that right here. I've got the line x over 2, and then we've got square root of x. This time, our solid cross sections perpendicular to the x-axis are rectangles whose heights are 3 times the lengths of the bases. Write but do not evaluate an integral expression for the volume of the solid. So rectangle is base times height. They also said the heights are 3 times the base. So h equals 3b. So I plug 3b in for h and simplify that, and it gives me 3b squared. So then I need to figure out what b is. B is going to be top minus bottom. So top is the square root. Bottom is the line. Then I plug that in to b squared and move the 3 out. There's the 3. Here's the b. It's squared. And then where these intersect are at 0 and 4. Next one, cross sections are perpendicular to the y-axis. So since it's perpendicular to the y-axis, that means I've got to solve for x. And we're dealing with semicircles. So as you see, I solve for x on that one. I solve for x on that one. It's a semicircle. The area of a semicircle is 1/2 pi r squared. I've got to figure out what r is. So r is going to be right minus left. So it's the line minus the square root. So there's the line. There's the square root. So 2y minus y squared. And then we have to remember, anytime we're dealing with semicircles, I always have to do top minus bottom or right minus left, and then divide that by 2. So then I take the 1/2 pi, put it out front. I take my r and square it. And then my limits, make sure my limits are y values this time, since everything's in terms of y. It went from 0 to 2. And I have completed that problem. Number 9, just some implicit differentiation. Derivative of y is y prime. I need the product rule here. First derivative of the second plus the second derivative of the first. Derivative of x squared is 2x. Derivative of 1 is 0. Then we want to plug -1 in. So I plug -1 in for x, plug -1 in for x. I need a y. Remember, if I don't have something, I go back to the original to find it. So I plug -1 in for x on both places and solve. We see that y is 1. So then I can plug 1 in for y, which is what I did here. I added that over. That gave me 2y prime equals -1. I divide. We get -1/2. On number 10, remember this is the same thing as the cosine x squared and then having the exponent of 5 all the way out here. So chain rule, I'm going to bring the 5. It's going to go to a 4. The inside stays the same. Then I need the derivative of cosine, which is negative sine. Inside stays the same. And then I need the derivative of the very inside, which is 2x. Clean that up. I get -10x cosine to the 4th x squared sine x squared. On 11, e to the -3x, I want to integrate it. So you can do a u for -3x. If I did a u for -3x, du is going to be -3. Notice there is no -3 in here, so that means that's why I got to have the -1/3. And if we integrate e, it's just going to be e. So then we plug in from 1 to 0. I plug in 1, I get e to the -3. I plug in 0, I get e to the 0, which we know is 1. Same type of deal here on this one. I could do a u for the 2x. Derivative of 2x is 2. There's no 2 in here, so that's why I need the 1/2. Integrate sine, we get cosine, and it's got to be negative. And then we're going from pi over 12 to pi over 8. I plug in 2 times pi over 8 is pi over 4. 2 times pi over 12 is pi over 6. Cosine of pi over 4 square root of 2 over 2. Cosine of pi over 6 is square root of 3 over 2. Again, I could have stopped here if I wanted to, but if you clean it up, this is what you end up with. On 13, we need to do u for sine of 5x. So u is sine of 5x. Derivative of that is 5 cosine 5x. I've got the cosine 5x. I don't have the 5, so that means I got to have a 1/5. So that's why I have a 1/5 out here, u to the 3rd. Integrate u to the 3rd, I get u to the 4th times 1/4. And then we plug in sine of 5x for the u. 1/5 times 1/4 gives me 1/20th. Sine of 5x to the 4th plus c. All right, 14. Consider the curve. And first of all, we want to show this. So that's just implicit differentiation. Derivative of x squared is 2x. Derivative of 4y squared is 8y squared. Derivative of 7 is 0. And then I have to do product rule with 3xy. So I factored the 3 out. I did first times derivative of the second plus the second times derivative of the first. I distributed the 3. And then we're going to get y primes on the same side. So I subtract that over. I move the 2x over. I factor out the y prime. And then divide by what's left. So that's part A. Part B, show that there is a point P with x-coordinate 3 at which the tangent line to the curve at P is horizontal. So x-coordinate of 3, so that means I'm going to plug 3 in for x. So I plugged 3 in for x here, and I found that there were 2 y values. Okay, one of those y values, since I'm doing a tangent line that's horizontal, when I plug 3 in and one of those y values in, I should get a slope of 0 since they want a horizontal tangent line. So I take those y values and I plug, and actually I only have to plug it into the top because in order for this thing to be 0, the top's got to be 0. So I plug both of those into the top. And when I plug the 3 in there, that gives me the 0 that I'm looking for. Or plug the 3 in and the 2, that gives me the 0. If I plug 3 and 1/4 in, that's not going to give me the 0. So that's the one we're looking for. All right, find the second derivative, and do we have a max, min, or neither there? So second derivative is going to require the quotient rule here. So bottom derivative of the top minus the top derivative of the bottom over the bottom squared. Okay, now we've got y prime in here, and we're doing it for the same point we did up here. Well, we know when we plug that point into the derivative, it's going to give me a horizontal slope, which means the derivative is going to be 0. So that means anywhere I see y prime, I know I can go ahead and put 0 in there because y prime at the point 3, 2 is 0. So I just plug 0 in everywhere I see a y prime. I plug the 2 in for the y, and I plug the 3 in for the x. And when I do that, I end up with negative 2/7. And it looks like I didn't finish the problem because the last part, does the curve have a local maximum, a local minimum, or neither at this point? And since my second derivative is negative, then that means my original function is concave down. So if I have a critical point and I'm concave down, then that means I have a local maximum. So I would say a maximum because this right here, the second derivative of 3 to the point 32 is negative. 15, graph of function f is shown. G of x equals that integral. So I want to find g of 0 and g prime of 0. So the first thing I'm going to do is plug in 0, and then I need the area from negative 3 to 0. So the area from negative 3 to 0, notice this rectangle is 3, this triangle is 1.5. Add those together, I get 4.5. Then we want g prime of 0, so that means I need g prime, which is the derivative of this. So that is the second fundamental theorem of calculus. 2 steps to that. I plug in my variable, so that's f of x, and multiply by the derivative of what I'm plugging in. I'm just plugging in x, so that's just going to be 1. All right, so there, that means g prime equals f. I want g prime of 0. So g prime of 0 is going to be f of 0. And if I come over here, here's 0, and we get a y value of 1. So that's why we get a y. We get f of 0 is 1. Part B, find all x values at which g attains a relative maximum. So if I'm looking at the derivative, I'm going to have a maximum whenever my derivative changes from positive to negative. And that happens right here at the x value of 3. So x equals 3 because f changes from positive to negative. All right, C, find the absolute minimum value of g on the closed interval from negative 5 to 4. So this one says absolute. 2 things you need to notice. It says absolute, and the other thing is value. So since it's absolute, then that means I need to check endpoints and critical points where there is a relative minimum. So that means I need to know what g of negative 5 is, I need to know what g of 4 is, and I have a minimum right here at negative 4. So that's why I'm checking g of negative 5, g of negative 4, and g of 4. I went ahead and checked g of 3 as well because it's a critical point. I don't think that's totally necessary, but if you've got time, you might do it because we know g of 3 is a relative max. A relative max cannot be a relative min. So I'm just finding those areas. So from negative 3 to negative 5, notice those 2 areas match up, so they're going to cancel each other out. So that's why g of negative 5 is 0. We go from negative 3 to negative 4. I've got a 1 by 2 triangle. So the area of that is 1. Since I'm going backwards, that means it's got to be negative. So g of negative 4 is negative 1. And then from negative 3 to 3. So we already know from negative 3 to here is 4.5. Then I need to figure out the area of these 2 pieces right here. So what I did was the area of the full rectangle minus the area of the semicircle. So the full rectangle is a 2 by 1, so that's 2. So that's why I have the 2 here. And then minus the semicircle. The semicircle has a radius of 1. So semicircle is 1/2 pi and r squared. So you see my radius there is 1. Okay. And then I have another 1 by 1 triangle, which has an area of 0.5. So that's why I've got the 0.5. When you put all that together, you get 7 minus 0.5. I go to g of 4. G of 4 is going to be the same as g of 3, except I've got to go minus that last 0.5. So So I had 0.5 minus the last 0.5 is going to give me 6.5 minus 0.5 pi. And my minimum, as you see, is going to be the -1, minimum value. Remember, when it says value, that means they want the y value. So my minimum y value is -1. And D, find all values of x in the open interval, -5 to 4, at which the graph of g has a point of inflection. So if I'm looking at the derivative, to get a point of inflection, the derivative's got to change from increasing to decreasing or vice versa. So that happens right here at the x value of -3. It happens right here at the x value of 1, and it happens right here at the x value of 2. So x equals -3, 1, and 2 because f changes from increasing to decreasing or vice versa. All right, 16. Let f be a function that is twice differentiable for all real numbers. The table above gives values of f for selected points in the closed interval. We want to evaluate this. So as you can see, the first thing I did was separate all this out. I took the 3 out here, I moved the 5 in front, and then I had f prime here. Okay, we've talked about when you integrate just a number, you can take that number times the difference in the interval. So the difference in the interval is 11, and 3 times 11 gives me 33. So then minus the 5. If I integrate f prime, that's going to give me f. So then I plug in 13 and I plug in 2. So f of 13, there's 13. F of 13 is 6. I plug in 2. So f of 2 is 1, which gives me that. So 6 minus 1 is 5. 5 times 5 gives me 25. 33 minus 25 gives me the 8. 17, oil is leaking from a tanker at a rate R of T, gallons per hour. So notice it's gallons per hour, which means I'm looking at a derivative where T is measured in hours. How much oil leaks out of the tanker from time 0 to 10? So we want to know how much oil. Oil is measured in gallons. So if I'm dealing with gallons per hour, in order to get gallons, that means I need to integrate. So I'm going to integrate that thing from 0 to 10, punch this in my calculator. There's my gallons. All right, last problem. 18. We've got a differential equation and we've got an initial point. First thing, write an equation for the tangent line that passes through the point -1, 2, and use it to approximate the value of f of -1/2. So tangent line means I need a slope and a point. So there's my point. They gave me a derivative. To get the slope, that means I just plug that point into the derivative. So that's what I did right here. That gave me a slope of 4. So y minus my y value equals 4 times x plus 1. And then we want to approximate f of -1/2. So that means I put -1/2 in for the x and I solve. F of -1/2 is approximately 4. Part B tells me between -1 and -1/2, the second derivative is less than 0, which means the second derivative is negative. Is the approximation you found in part A for f of -1/2 an underestimate or an overestimate? I do that by considering concavity. So we have a second derivative that is negative, which means my graph is concave down. So concave down is going to look like this. The tangent line is going to be sitting above it. Since the tangent line is above it, then that means my approximation that I found is going to be above the original graph, which then means it's an overestimate. So I'm going to say overestimate because the second derivative is less than 0. And then finally, find the particular solution to the differential equation. So that just wants me to separate, integrate, find C, and solve for Y. So first thing I did was factor out the x squared. That's kind of the trickiest part of this whole thing because it's tough to see what to do to separate it. But if you factor out the x squared, then you can see that the 6 minus y needs to go to the other side and x squared dx stays on the right side. So if I integrate x squared dx, I get 1/3 x cubed plus c. Over here, notice this stays in the bottom because the exponent of it is 1. And if I have an exponent of 1 in the bottom and I integrate, that's going to give me the natural log. Don't forget about the negative. Remember, you got to keep an eye on this. If my variable is negative, I got to have a negative out in front of my natural log. All right, then we're going to plug in our point, which is -1, 2. So I plug in 2 here, I plug in -1 there. We get C is 1/3 minus the natural log of 4. So I plug that in for C here. There is only 1 point left, and that's to get Y by itself. So I move the negative over to get rid of the natural log. I do the E. So since the natural log of 4 is here, when I do E, that makes it just 4 in front. These two have to stay in the exponent. To get rid of the absolute value, I have to do plus or minus on the other side. And then I'm going to do 2 things here in the last step. I'm going to subtract 6 and multiply by a negative, so that makes the 6 positive. And then I have to choose whether or not I want the plus or the minus. I chose the negative here because when I plug in -1, I have to get 2. So if I plug in -1 here, that's not right. Is it -1? So my signs are off here. That 1/3 needs to be negative. Yep, I forgot to change that. So when I move this negative over, that right there should be negative, which means this should be negative, and that should be negative. Anyway, so this is going to go to 0. E to the 0 power is 1, so I've got 6 and a 4. In order to get to 2, I've got to do 6 minus 4 instead of 6 plus 4. So make sure you make that correction there. That should be a minus. All right, so that's your answers to AP test review number 7.